The next logical step is to look at how you could return a value from a delegate, or even how to use parameters. In our example, we had two methods, which in reality would depend on the order to successfully operate. The method that tells the warehouse to get ready and the method that sends a confirmation email would both need to use the order to know what was processed. Ideally, we'd like to get the order passed as a parameter to these methods. To allow a value to be passed as a parameter to a delegate, the method signature needs to be changed. Head over to the order processor. We can change both of the delegates to indicate that they require a parameter to be passed to them. Now, both the order initialized and process completed both specify that methods that correspond with this delegate need to require an order to be passed as the first parameter. We will now get a few errors in the solution because we are no longer invoking the delegates in the correct way. As you'll see on the invoke method call, it requires the order to be passed. This is a quite simple fix. All you must do is pass the order into the invocation, just like you would if you called the methods directly. Let's just take a moment to appreciate what's going on here. We've defined a required method signature for what really is a function pointer. This class expects this function to be referenced, and as long as it's not null, it will invoke a method that it knows nothing about, doesn't know more than only the method signature. When the application runs and this code path is executed, it will delegate the work to that referenced method. We're passing the order that we are currently processing into both of these delegated method calls. If you try to run the application, you'd notice that we still have a couple of errors that we need to attend to. The method signatures in the program does no longer correspond with the delegate that we have defined. Again, this is a simple fix. The method that you reference needs to have the exact same method signature as declared by the delegate. Thus, add the order as its first parameter to both of these methods. Now, the errors disappeared. This lets you use the order that is passed from the order processor and act accordingly on that. You can see that you didn't have to change anything where you pass the method as a reference. All you need to make sure of is that they have the correct method signatures. This approach provides flexibility as you can introduce functionality that shouldn't live inside the order processor. As I mentioned earlier, there are other patterns and practices and many ways to achieve a similar extensibility. At the end of the day, it all comes down to what you prefer. One thing to keep in mind is that when you invoke the delegate, it's like any normal method call. If you throw an exception, for example, it's not going to automatically be caught. You'd have to handle that just like you do with any other method call. For example, you could wrap the invocation in a try and catch block. All this approach is doing is delegating a method implementation to the external consumers. If you want to rely on the outcome of a delegated method, you'd most definitely want to use a return value. Just like adding a parameter, adding a return type is just as simple. You'd go ahead and change the delegate declaration to your preferred method signature. This can return absolutely anything. Change the order initialized delegate to return a Boolean. Then we are going to slightly change how we invoke this. If we don't have an instance of the delegate, we'll do nothing. If the invocation returns false, something went wrong with the initialization of the order. We can then throw an exception. While unlikely, I do want to highlight a potential race condition. If you use the null conditional operator, you don't have to worry about this at all. This is because when you use the null conditional operator, it will automatically create a local variable that represents the delegate. After that, it performs a null check, and then it invokes the delegate through that local reference. Why does this matter, you might ask? Delegates are immutable, just like strings are. To change them, you have to point to a new reference. This is why storing the reference inside the method that performs the null check and then performs the invocation prevents a race condition, because that locally captured reference cannot be changed at any time while this method is being executed. As long as you use the null conditional operator, this will be handled for you. If you compile the application, we again get a compiler error that tells us that we need to update the method signature in the program. Change send message to warehouse to return false, and run the application with the debugger attached. You can see that we get into this method, it returns false, and we'll get an exception thrown. You've successfully added both a parameter and a return value. You can change this to return true instead, and then rerun the application. I'd suggest that you experiment on your own with what we've just learned. As another fun experiment, you can go ahead and try what happens if you return a delegate from a method. Since a delegate is used just like any reference type, you can specify that the return type is a delegate as well. Simply return a method reference that corresponds with that delegate, and whoever uses this method will be able to invoke the delegate that is returned. You can then use this returned delegate and invoke that. You could call invoke or use it like a normal method. Personally, I prefer using invoke, especially in this case as it would make it a little bit more readable. I'd really recommend that you pause the video and experiment with delegates on your own. Please remember that if you run into any issues, I'm here to help. Reach out on the discussion board at any time. Next, we are going to be looking at how you can construct a chain of delegates and invoke multiple methods with a single delegate reference.